So let's start with what's eigenvalue in quantum mechanics. The term eigenvalue is used to designate the value of measurable quantity associated with the wave function. I can repeat it again. The term eigenvalue is used to designate the value of measurable quantity associated with the wave function. You know the wave function is psi, and the value of the measurable quantity is the eigenvalue. Suppose if you do want to measure the energy of a particle, you have to operate on the wave function with the Hamiltonian operator. So in this connection, eigenvalues and eigenvectors are used in linear algebra in mathematics. But in physics, these are widely used for vibration analysis, simple harmonic oscillators, matrix diagonalization, and atomic orbitals. As we all aware now, the meaning of eigenvalue and eigenvector. Eigenvector could also be called as eigenstate if we want. Depends on what operator and what observables you are considering. If the operator is now a Hamiltonian, the eigenvalue you get will be the energy of the system, and the eigenvector tell you its state. So far, the simple harmonic oscillator system, the eigenvalue of the Hamiltonian is equal to n plus 1 by 2 h cross omega, and n depends on the system's quantum states, and the eigenvector in simple harmonic oscillator is just the eigenstate. And in most cases, you can consider the linear combination of the vector as a wave function. That is, the eigenvector gives out about what its state, and usually it will include some probability in its coefficient, since we usually get more than one eigenvector. Again I say eigenvector, here you can call it as eigenstate. So we can, as we had this simple harmonic oscillator as one example, we can also have the infinite potential well. If the operator is observable A, now the eigenvalue we get will be the possible outcome of A, and the eigenvector is the state corresponding to the outcome. While if we use the Hamiltonian H in the above case, we will get is equal to n square pi square h cross square by 2ma square. Here in the infinitely deep square well, this above equation is equal to n square pi square h cross square by 2ma square is the eigenvalue equation. So these two examples, as I hope, will serve the purpose of understanding eigenvalue in quantum mechanics. So now we can go for number of examples as this simple harmonic motion or this infinitely deep square well. And we can answer for a lot of questions on eigenvalues. There are some example questions are as follows. So you can ask what are the properties of eigenvalue. You can also ask, can eigenvalue be negative? You can also ask, can an eigenvalue be zero, and etc. The Schrödinger equation is an eigenvalue problem itself. So try to work on eigenvalues. It started with mathematics, linear algebra, and it has its own transformation in quantum mechanics in this time. We will see you in my next video clip on the applications of eigenvalues in quantum mechanics. Till then, bye.